Sabaha Nur, everybody. Welcome back. We're going to jump right in. And I just did a lot of talking that was maybe nonsensical for a moment, but we'll get through it. We are going to jump right in. Yesterday, we defined these sum and difference formulas to work through some wonky trig stuff as it may show up. Today, I'm going to go take attendance here in just a moment. But what I would like to do right off the bat is I'm going to keep these up on the board. I want you guys to do a couple of these. Now, I'm going to have you do two of them. And we'll do the easier one first, although the problems are exactly the same. There's one little part of this that, for whatever reason, the math and the concept doesn't click nicely in my head. Doesn't mean it won't for you. It's just never clicked for me as I try to explain it. So I might ask you guys for help with that. The first thing I want you to do is find for me on example A, and we're just using these. I want you to find for me an exact value, which means not a calculator. I want the sine of 15 degrees. And I'll move that here in a second. And then on B, this one, same sort of problem, but let's go ahead and make this the cosine of, anybody have a calculator in front of them? Will you math frack? Ooh, is this going to work? I lied. We're just going to say the cosine of 7 pi 12ths. I'm sorry. I just changed my mind. Cool. Together, I want you guys to reason through this. I've not told you anything other than these are the formula. I will give you a moment. I'll go knock out attendance. And realistically, probably a couple moments, I would guess. But why didn't that select? There we go. Cool. Sine of 15 degrees is the one that I want you to do first. I'm looking exact values, not approximations from your calculator. Sweet. Play around with that. We'll come back. JV, if you're watching this, I want you to play around with both of these and resume it when you're ready to see it. And I will continue talking in 3, 2, you know what to do. All right. So, with problems like these, I'm not going to expect you to show it like exactly like I do every single time, but I do think that there's benefit in showing it. First thing that I worry about is this 15 degrees, it just doesn't show up on the unit circle, right? So I need a better way to think about the sine of that angle. Now, it turns out there are a crazy amount of options to do this, but I think that I saw everybody who made this first decision. Are there any two angles that you can either add or subtract to get to 15 degrees? You could do 45 minus 30, right? Okay, alternatively, could you also do 60 minus 45? Or, and it's weird, but you could do 330 plus 45, and that would get you to the same ending point at 15 degrees above. Like, there's so many different ways you can combine these. The first step that I would encourage you to do always, but I'm not going to count you wrong for it, is let's just rewrite this. Instead of saying it's the sine of 15 degrees, I'm going to rewrite this instead, and I'll go with what you guys did. 45 degrees minus 30 degrees. Does this still say the same thing? It just looks a little different. Like if we did the parentheses, it's still the sine of 15 degrees. Now, I will try my very best to keep consistent here, but this kind of looks exactly like one of these. Specifically, I can think where this is alpha, which means if that's what we go with, this must be beta. Cool. So when we run through this then, let's just plug and chug. This is the sine of a difference. So we're going to apply this formula right off the bat. And sine is nice because it doesn't change, right? Plus or minus stays plus or minus. So it's sine alpha cos beta. And I lied. I'm not going to change colors as I'm writing this because it's just going to be way too many. So the sine of alpha, which is the sine of 45 degrees, times the cosine of beta, which is 30. And then do I subtract or add here? I subtract. And now it's the sine of 30 degrees times the cosine of which angle? 45. And we're just plugging in alpha beta. Now, Riley, you mixed ideas, which it's okay because the ideas that you mixed, they're so close to exactly what we need. I just want to make sure we can clear that up. What is the sine of 45? So careful, because you're just giving me the angle in radians. What is the y value at 45 degree angle? Good. So what you were plugging it in for this argument, but you were doing it and then plugging it back in. You just did everything. You were trying to skip this step, which I don't mind. The sine of 45 is root 2 over 2. And we're going to multiply this by the cosine of 30. And these ones I will just arbitrarily change colors. Somebody hook it up. What is the cosine of 30 degrees? Try again. Remember, it's further to the right. Sorry, further to the right than up. 30 degrees is that first point. I'm way further right than I am up. So you had the right point. You just took the wrong value because the cosine is always the x. So here we are, sorry. Do you see that, Sean? Yeah. Okay. Minus, what's the sine of 30 degrees? 1/2. There's that 1/2 that we're after. And finally, the cosine of 45 degrees is root 2 over 2. And it's an ugly calculation, but especially since we're going for exact answers, it's actually nicer and easier than using your calculator for it. Because what do you notice every denominator is? 2. And it doesn't really matter because we're multiplying, but when we subtract, we're going to get a common denominator anyway. Anyway, weird. All right, so we kick forward just a little bit. I'm going to put my equal signs here because it's bugging me that they're not there. And then let's just calculate out. What's root 2 times root 3? Root 6 over, what's in the denominator? So it would be 2, but when we multiply, they have to multiply. So it's over 4 minus 1 times root 2 is root 2. And that's also over 4. And I would only go one more step. And I'm really curious how you guys interpret this and just to see how much you remember about radical stuff. How do you think I should rewrite the numerator here? Because you did root 6 minus root 2 is root 4, right? Okay, before we commit to it, let's just check something. If I did root 4 minus root 1, and that rule worked, it should come out to be root 3, right, Bea? But let's check it. What's root 4? Minus what's root 1? So they don't give me the same answer. This doesn't work. When we deal with radicans, just like fractions or like terms, we have to have the same thing underneath each radical. Super easy mistake to make because a lot of stuff does work like that. Radicals are not 1. Does that make sense? Okay. All right. So instead, we can't really change it other than making a single expression. It's root 6 minus root 2. That's it. That's my exact answer. There's no more simplifying that has to happen. We can't make the radicans agree to simplify further. We're done. These problems wind up being really helpful in finding specific angles. However, they don't really feel like math to me. They feel like just plugging and chugging, which is not a fun way to do math. Might be an easy way to do math, but it's less interesting for me. Okay. Thoughts, concerns, issues. Is it easier with or without a calculator? Obviously, it's easier with, right? Because you just get the approximation right off the bat. Dumb question. All right. So here is the part that I struggle with. And I have a way around it. 7 pi 12ths. That's above 90 degrees, right? Okay, there are two approaches that one could take. Could we take this and right away change it to an angle in degrees? Like, is there a way to convert from radians to degrees? We could. And if that's the route that you pick, I'm okay with it. However, I'm hopeful that you guys have enough of the unit circle around that you at least know a bunch of the radians that show up. None of them are over 12 right off the bat, right? Like the first one's pi 6. So I'm just going to make a little list. And I usually think this in my head, but it might be helpful here. So just some like scratch work to think it out. Pi 6, could you write it as something over 12? So we could get a 2 pi 12ths that shows up on the unit circle, right? That's my pi 6th. So does pi 4ths, which is 3 pi 12ths, because I'm just multiplying by 4 over 4. Pi thirds would be 4 pi over 12. Now, by just doing the first quadrant, without ever having to do the change to degrees, do you guys see a combination where we can make two nice angles turn into 7 pi 12ths? Now, I can't see this if I don't do the over 12 part. Like, on my notes, it specifically says this is pi fourths plus pi thirds. I don't do that fraction in my head. I don't know why it doesn't click, but it clicks if I do this. Okay, so with these from quadrant 1 just changed into over 12s, somebody hook it up. What is a good way that we could rewrite 7 pi 12ths as? Do you agree it's this one and this one as the ones that need to combine? Now, I could write 3 pi 12ths plus 4 pi 12ths, and that's completely fine. But 3 pi 12ths doesn't show up on your unit circle, does it? Not directly anyway. What's a better way to write 3 pi 12ths? This is just the cosine of pi fourths plus 4 pi 12ths is pi thirds. If you are listening to me going, I don't like this, I hate it, you are completely fine to switch to degrees first. I think that this is faster. It'll be more efficient instead of converting every time. But you can. As soon as we have this, I have the cosine of a sum. So we use the sum formula. I want you guys to write out your, expand this. And by expand, I mean just apply the sum formula for this. Expand this. And I want to come, I'll wheel around and look at your work. Cool. Did you guys come up with the same expansion? Cos pi fourths, cos pi thirds, and then really important, minus sine pi fourths, sine pi thirds. Because remember, plus or minus changes to minus or plus. At this point, it's just going to be how comfortable with the unit circle are you to make this a short or a long problem. Now, for stuff, I will commonly skip this line. As long as I've identified alpha and beta, I will often skip this one. But as with everything, the deal is if you skip it and you can do it and I can follow it still, I'll still give you credit. But if you skip it and get stuff wrong, partial credit's gone. So it's really a choice of based on your confidence levels. So here we go. We need 4 values, and we have at least 4 people. Fern, what's the cos of pi fourths? Root 2 over 2. Riley, just kidding, I already called on you. Mickey, the cosine of pi thirds? 1/2. Minus, Rafa, what's the sine of pi fourths? Good. And Huggins, how about the sine of pi thirds? Love it. Now, same thing is going to wind up happening. And realistically, if you're using these, pretty good chance you're going to get over 4 is what's going to happen. They're all going to have 6s and 2s. They're going to look really familiar. Is it too big of a stretch to go from this step to a single form? Denominator is going to be 4. What's in the numerator? Root 2 minus root 6. Okay, notice super duper similar forms. They should be pretty similar because cosines and sines are all cyclical and they're just shifted a little bit. Okay, yes ma'am. So that's a bigger question. Are you talking why did I change this plus to a minus? Yes, so we can dig into it. I'll come talk to you about it, and we'll talk to everybody about it, I'm sure. We never did the proof. So for this, remember that plus or minus changes to minus or plus stuff? I'm just following the formula. We didn't go into where the formula comes from and showing that it really works. I'm happy to expand on it, and we can look at the proof. But for this point in time, I'm going to say because the formula switches signs. Like, it is the way that it is, and I hate that as a math statement. We should probably just prove it, huh? Or at least look at the proof. We don't have to formally prove it. Let's check it out. Okay, let's do one more before we check it out, though. Do we have a weird one? Ooh, I like this one. Okay. This is going to seem like a throwback question, and it is. Is sine even or odd? There's a 50% shot at that. Huggins says even. Imagine the graph of sine as a wave in your head. Does it reflect over the origin or does it reflect over the y-axis? So again, another 50% problem there. Okay, does sine start at 0 or 1? So sine does this, right? Which means it does this on the other side. That is not exactly reflected right here. It's odd. Sine is an odd function. Now, the significance that sine is odd, remember, it means that if I wanted to calculate out the sine of -5, and we're not doing this right now, I'm just talking, -5 is gross because negative angles are ugly to deal with. But the fact that it's negative means that we're going to get the same value just flipped. We can do this on that function. That is the value of having even and oddness. So I don't have to worry about the negative. I'll just move it out front and deal with it after the fact because of the symmetry that we get over the origin. I want you to keep the fact that sine is an odd function in your heads while we do the next problem here. So one more that I want you guys to check out. And let's see here. I want you to do, what do we do first? We did sine of 15. Is cosine even or odd? Even. Okay, so we're going to actually use that fact. I want you to find on C the cosine of, let's say it's negative. Do you want degrees or radians? Degrees because they're easier? Pi 12ths. Cool. Cosine is even. You may or may not use that. I'll give you guys just a moment, and I'm going to get the proof worked out for us here. So I've elected to use the fact that cosine is even to get the negative rid of it so I can just work with everything positive. And then, like I said, when I'm normally doing these, I won't show that middle step where I'm plugging everything in. I know it's cos pi thirds, cos pi fourths, plus we change signs, sine pi thirds, sine pi fourths. So typically as I'm doing this, I'm just going to jump right in. Cosine of pi thirds is 1/2. Cosine of pi fourths is √2/2. It's a plus because cosine does this wonky thing where we'll just now do the signs. Sine of pi thirds is √3/2. And the sine of pi fourths is √2/2. And lo and behold, we get a very similar answer to every other single problem that we get because we use the same angles every time. It looks like it's going to be √2 plus √6/4. Now, if there are people, am I right, first of all? I didn't even check. You get something different.
Yeah, would it, because Israeli did pi 6.
So let's look. You did pi sixth minus pi fourths, right?
Yeah. Okay.
Oh, you actually did probably pi fourths minus, no, pi sixth minus pi fourths.
Reverse.
So, yep, so the order looks a little bit differently, right? But I'm going to do the same thing. I didn't get rid of the negative here. I didn't use the fact that it was even. And I'm just going to think through it the same way. I know it's cos this and cos this. So cosine of pi sixth is still a √3/2. And cosine of pi fourths is √2/2. Minus sine of pi sixth is what, 1/2? That's a tiny 1/2. And √2/2 again. Does this look like your work? Okay, so if we go one step further, we get √6 minus √2/4. Okay, now as we look at this, these answers look wildly different. Are they? What do you guys think? Are they different? They look a little different. How do we even begin to think and determine whether or not they're really different or not? And what did I possibly do wrong? What's weird about the cosine expansions for sum and difference? Plus or minus changes to what? Minus or plus. This was a minus here. This was a minus. Hey, that better be a plus. And look, they're the exact same.
How does it be even?
So if you think about cosine, no matter where we are, cosine starts like this, right? So if I were to say, hey, find me the cosine of positive pi fourths right here, this is what it spits out at me, right? What about the cosine of negative pi fourths? Yep. Careful. Remember, if we're looking at the graph of cosine, I plug in an angle and it spits out a value. So whether I plug in positive or negative pi fourths, it was the same y value, right? So that's what I'm making use of to get rid of them. If you don't like it, that's okay. You don't have to use it. Totally good with not even thinking about the evenness. Okay, cool. All right, so we're going to talk through a proof here. And I'm not going to make you write it down, just so you know, but I do want you guys' attention with stuff. And it's not a threat with anything. The proof stuff I know you guys love, but we just don't have the time to prove everything all the time. Okay, so they take a very algebra approach to this. They put a couple pieces on the unit circle. So they said, hey, here's angle U that ends at this point, x3, y3. Okay, it's just some arbitrary point wherever it is. Okay, they also had angle V, this is our alpha and beta, that ended at this point, x1, y1. And then they said if you subtract them, you get somewhere in the middle. Okay, so we've just assigned coordinates to an angle minus an angle and saw where it took us on the unit circle. Okay, from here, we got all this stuff going on. And if I were to take these distances or these formulas, what are these representative of? x2 minus 1 and y2 minus 0. And I'm going to give you guys a second to read through this. I'm going to actually do this so we can see a little easier. I need to know y, 1, and 0. So, can you expand on that a little bit?
The x and y are supposedly cosine and sine, and when you put sine minus not sine, cosine minus 1 turns into sine squared.
So, careful. It has to be cos squared minus 1. But I like your idea. I like where your head's at. Now, as we're looking at it, they do have another circle here. And I wasn't trying to intentionally mislead you. If you take the distance across these two, it winds up being the same as this distance, which is they just draw the arcs down here. Or the chords, I'm sorry. Okay, so we draw our chords, and when we see 1, 0, they're simply finding the distance. This is the distance formula. They're saying, hey, let's find this distance right here. Okay, so they do it, which is from this point to u minus v is where that took us. And they say, hey, let's find the distance here, or the difference between these points, which is a distance, right? So they calculate it out here between these 2 points. And what we wind up finding is that this x value is this product, which is ugly. Now, this is page 296. It's kind of ugly because of subscripts, but check this out. x3 was the x coordinate when we rotate u, right? So the x coordinate of a point on a circle, is that cosine or sine? It's cosine. So when we get to this expression that says x3, I could just call that cosine of angle u. Everybody cool with that? Can't get a read on you. Lots of blanks. Okay. When I see the point x1 and I look at it right here, it's the cosine of which angle leads me to point B? V. So instead of x3, x1, we could write cos u, cos v. Okay. Now, to get to this next part, when we add these up and we simplify and solve for x2 like they've done here, we get y3, y1, which is just the sine of u and the sine of v, and we wind up seeing graphically that these must be added together. Okay, we're not going to go into the nitty-gritty part of it. I will not make you guys do a proof. This is what really formal proof looks like. I would do it much shorter than this, but it's nice to see that it does actually work out. By saying these distances are the same and solving for x2, the only outcome is that they wind up adding if we came from a difference, Riley. Which I know that's probably not super satisfying, but hopefully this is better than just saying because it does. Like there's a mathematical justification, page 396. All right. Feeling good? I am just dying to learn something. You guys have 60 seconds. Ooh. You guys good at trivia? Okay. You are? I think I'm pretty good at trivia, as long as it's not pop culture. 60 seconds. I want to learn something new. You need to discuss with each other. Tell me something I don't know. So, there are some fun variations of problem types that we can have. And these problems, they're computationally, bleh, like plug and chug math is not the most interesting. Do we need a whole homework set of just doing practice with these formula? All right, so in lieu of giving you a single assignment where I just say, hey, use these formulas like 10 times, we're going to keep trudging. And we're going to use these ideas to go a step further on an idea that we've already seen. So we're going to have another example. And I don't know that we're going to get to homework tonight. So hopefully that doesn't break your heart too much. I want us to evaluate. And that's it. I'm going to give us a little series of like instructions or parameters, restraints, constraints, you might say. Some things that my problem has to meet. And I'm going to ask us to find some stuff. So here we go. I want us to find the exact value, and I'm not going to write that, but I want to find the cosine of, I'm going to call it u plus v, which we've been using alpha beta, but it doesn't matter. As long as you have two angles, it's okay. So I want us to find the cosine of u plus v given the following information. And I'm going to tell you two bomb pieces of knowledge. First of these is that if you were to take the sine, and I'm going to switch colors here for a very particular reason. If we were to take the sine of angle u, well, it's 12/13. Okay, so there's our first little part. But more than that, I'm given that the sine of u is 12/13. And I'll even go a little bit more specific, but I think you would probably assume this, where we're just going to say that this is in quadrant, let's say quadrant 1. Quadrant 1. Okay, and beyond that, we also know that the cosine of angle V is equal to negative 3/5. And that this cosine happens to live, or angle V rather, and I'm going to word this one differently, is stuck between pi halves and pi. Okay. We have a lot going on here. Right off the bat, we have a formula for this. And whether you need to write it or not is entirely up to you, but I'm going to write it either way. So immediately, do I have a way to expand the cosine of u plus v without knowing anything else? Like I don't know u and v yet. Is there a rule that we can follow? Let me, gosh, yes or no questions every time. Charles, if you are given the cosine of u plus v, what is the rule that we can use to expand this guy? Cos u times the cosine of v. Love it. All right, so here's our rule. Now, whether you have this written down as the rule, like in this problem, entirely up to you. The more you write it, the more it's just going to get stuck in your brain. Do we know the cosine of u right now? I don't. I know the cosine of v, so I already have that one, and I know the sine of u. Those are the only two things that I know currently, which means we need a way to get the cosine of u and the sine of v. Like, we need those. So let's just do a little thinking here. Anytime you're doing trig stuff, if you imagine stuff in your head, and I don't know if everybody does, when I say trig, what does it make you think of? What sort of shape? Triangles or circles, probably, or triangles inside of circles. Does this sine value correspond to some triangle that exists? And I know on that triangle, I know two of the lengths. It's in quadrant 1, so I'll draw it as such. And let's say that this is angle u. What lengths do I know on this triangle based on the information we're given? The hypotenuse is 13. And the opposite is 12. And oh my triples, anybody remember this one?
15? No.
Can't be 15.
14.
So it can't be bigger than the hypotenuse, right?
10.
Are we guessing? Okay, can you square 13? 169. Can you square 12? What's 169 minus 144? 25, and its square root? 5. That was a Pythagorean theorem that we just ran through without writing it down. I would just encourage 5, 12, 13. So as soon as I get this, notice I need the cosine of u, right? So I'm just going to make a little note here and say, okay, well, the cosine of u, because this is angle u that just caused this triangle, what's the cosine of this triangle? Or this angle, I'm sorry. 5 over 13. And you can think of this in one of two ways. They're the same thing, just different language. You can think about the cosine as being the adjacent side of the hypotenuse, or 5/13. Or if you'd rather, as long as you realize that this is the origin, the very center of my unit circle, or a circle in general, cosine is x over r. So I can see that represented in both situations. I want you guys to draw me this triangle as well. Find me the sine of v once you've drawn this triangle, and then get me the entire expression. Without me here, the context would be weird if you're watching this video and you're not my student. Bow ties and butterflies. Use it. I'll give you guys a second. So we're in quadrant 2, right? Have to be based on this. This is just a fancy way of saying quadrant 2. I just want to make sure we had both ways of thinking about it. So I put my point up here for some reason. I don't want to draw my triangle in this little tiny space. Here's the center of the circle. This says go up, or sorry, down 3 or left 3 if it's cosine. Left 3, I think, right? So there's my -3. And then my hypotenuse is always positive. And Pythagorean triples hook it up. This is angle V that we're dealing with. What is this side? 4. Okay. I have cosine of u. We already worked that out. The only thing I need left is the sine of v. From this picture, can you tell me the sine of v? So is opposite over hypotenuse. Is it 4/5? As soon as we have this, we have all 4. Everything that we need to evaluate this expression is in front of us right now. Now, I didn't rewrite the other ones because I'd had them listed here already. In previous years, I might have gone through it and said, hey, here's my given information that I had just so I don't lose track of it. There's the sine of u, and I was also given the cosine of v, I believe. Everything's changing here. I don't know why. Cosine of v, and I'm just rewriting these below. As soon as I have these, it's just plug and chug. Every time, it's just plug and chug, which is either awesome or terrible or a little of both. I don't know. So here we go. Cos u is 5/13. What was cosine of v? -3/5. And since it's a plus here, it's minus. And let's just run through. What's the sine of angle u? 12/13 times the sine of v is 4/5. Now, something similar winds up happening here. We get the common denominator right off the bat. It is given immediately. Okay. Let's just do it. Can you guys tell me what the denominator is going to be for everything? 5 times 13 is 75, right? 65, right? Okay, so let's see. I'm going to do an intermediate step here just so I can show it. 5 times -3 is -15 minus 48. Looks like it's -63/65. Assuming that my math is right. Feels right. Cool. I am real close. Really close to recognizing that u plus v is almost pi radians. Like, it's almost 180 degrees because, remember, cosine is -1 at that point, and I'm really close to it. If you ever find a value for cos u plus v or sine of u plus v or minus, doesn't matter, that's bigger than 1, you are wrong. Okay. Yeah, if you ever evaluate cosine or sine of something and you get a value bigger than 1 for the actual cosine without a number in front, you're wrong. Because sine and cosine only ever get as big as 1 or -1. Okay. I want you guys to do one more of these, and I think this is where we're going to chill out here. But we're going to make it more fun. Okay. Do you guys all have your trig sheets in front of you? Okay. Is there one of them that says power reduction? There's not one. Okay. So, the reduction formulas, I'm just going to tell you, they do exist. Yep, they're on that one. I only include the ones that we use regularly. I have one problem that I want you guys to work on right now, and then tomorrow we're going to have a ton of time to look at stuff and maybe do a little bit of paper folding. So hold on. Let's take your expectations for the level of fun that it's going to be, right? Take them, and then do your best Paul Bunyan impression, so that I'd rather you be overwhelmed rather than underwhelmed by the experience tomorrow. Like Paul Bunyan, not this one. I don't know how much. He chopped down trees, right? He had a big blue bowl. This might be a little piece of Americana that. Anyway, here we go. For the next 3.5 minutes, you guys are going to begin and finish this evening with an attempt at the following. You're going to solve. What? All right. So what you guys get the privilege of solving is only on 0 to 2 pi, which is nice. But here we go. I want you to solve for me. Determine when it's true that the sine of x plus pi halves lost my spot, sorry, plus the sine of x minus 3 pi halves. I want you to find me any angles x where this is 1. And we are only working on one circle, so no 2n pi's needed. You are solving this for x, and it looks ugly and terrible. It will not stay that way as long as you try something. Cool. I'm going to give you guys a couple minutes right now. At the start of class tomorrow, I'm going to make this 1-point homework, and I always say this and I never carry through with it. I am going to check it tomorrow. I want to see work, whether it's the right answer or not what I'm after, but I do want to see that you guys have tried this. But they're not like terms yet because they have different arguments. So you're going to have to change something. Something. Huh. Cool. All right. Everybody have this written down? Okay, just do it in your notes. I'll check your notes tomorrow. I'm going to pause it here, and then I'm going to mute my screen. And I'm going to solve it so I don't forget to do it. Cool. All right.